Bismillahirrahmanirrahim. Welcome to another lecture on supply chain modeling. We were discussing production planning and control, that is our module 4. In the previous segments, we had discussed how to make a production plan and then how to convert that into master production schedule. And we also discussed how to make a master production schedule. The next topic is material requirements planning, or MRP. The learning objectives of this lecture are to make you understand where MRP lies in manufacturing planning and control system, understand the purpose of MRP, understand the role of 4 inputs to MRP, and we will see one of those inputs is master production schedule. Understand the basic concepts in making a material requirements plan. So there is some terminology that must be understood, like lead time offsetting, planned order release, planned order receipt, schedule receipt, and so on. And we will solve a number of examples to learn how to make a material requirements plan. And finally, we will discuss a very important variant of the standard MRP that is generally mentioned in textbooks is bucketless MRP. So that is something that is actually used more practically. So we will see what is bucketless MRP and how it is used. So in part A, we will discuss some basics of material requirements plan. So we have repeatedly seen this hierarchy of production planning and control. So first there is a business plan, then that business plan is converted to production plan. Production plan is converted to master production schedule, and we also discussed that this production plan is for product families, master production schedule is for end items, and then we have material requirements plan. So based on the MPS or master production schedule that we made here, that was for end items, and we decided which end item is to be made, when, and in what quantity. So based on that plan, we plan for the components and raw materials for the end items, and that is called material requirements planning. So the logic of MRP is very similar to master production schedule, but the purpose here is different. So here we will be focusing on components and raw materials. So as we have seen this figure repeatedly as well, so we have seen that business plan is having long planning horizon, but level of detail is low. Production plan for product families is having relatively smaller planning horizon, but level of detail is relatively high because we were talking in terms of dollars or in terms of some broader units when we discuss business plan, but in production plan, we are talking in terms of volume of certain product family. MP is focused on end items, and the level of detail further increased, but planning horizon is relatively small. So MPS is somewhere in the middle in this production planning and control hierarchy. So in MRP, we are of course having higher level of detail because we are talking about components and raw materials, and planning horizon is here relatively shorter than MPS. So MRP is more commonly used in certain manufacturing environments, primarily those with push rather than pull systems. So this is important to be kept in mind. So it is primarily used with push rather than pull systems and with dependent demand rather than independent demand. So MRP establishes a schedule showing the components required at each level of the assembly. Based on lead times, it also calculates the time when these components will be needed. So which components are needed and when they are needed. So in summary, MRP determines what to order, how much to order, when to order, and when to schedule delivery. And these decisions are related to components and raw materials. So MRP is one of the inventory management approaches. And as we have mentioned in this slide, that it focuses on a dependent demand. So there are other approaches to inventory management as well that we will discuss in our module on inventory management. So we have already discussed this point that independent demand is the demand that is not related to the demand of any other assemblies or products. So it must master production schedule items are independent demand items. So the topic that we discussed, the last lecture focused on these types of items. However, since dependent demand is directly related to the demand for higher level assemblies or products, it can be calculated. So material requirements planning is designed to do this calculation. So that is our today's topic. That is how we can plan the dependent demand. In the figure is shown a product tree for a table. So this table is independent demand item. So its demand has to be forecasted, and then its production, or when actually it should be made available, is planned in master production schedule. So that is something we discussed in the last lecture. So that last row of MPS actually becomes first input, or one of the inputs to material requirements planning. And the demand for the components or sub-assemblies for this table, like legs and ends of the table, sides, top, and hardware, and that is the dependent demand, and that has to be calculated, and that can be planned using MRP. So there are 4 inputs to MRP systems. One, as we have discussed, is master production schedule, or MPS. The second is inventory records. The third is bill of material, and the fourth is planning factors. So these are the 4 inputs. Master production schedule tells the gross requirements for the end product, and based on that we can use the process of offsetting and explosion to plan for the demand of components and raw materials. Bill of materials tells us the quantity of different components and sub-assemblies in one end product, and when they should be required. When in terms of manufacturing sequence. We will see this point in some detail. Inventory data or inventory record shows the record of inventory of certain item, and planning factors focus on certain planning related decisions like safety stock, lead time, etc. There are 3 main outputs of MRP process. One of them is schedule of planned production. So schedule of planned production order releases. The second is schedule of planned purchase order releases. So if the component is being manufactured by the organization itself, the output will be the schedule of planned production order releases. And if that component is being purchased, the output will be the schedule of planned purchase order releases. And the third very important output is action messages or exception messages. So during planning, you come up with some extraordinary circumstances, or when things don't go according to the plan, or something happens that requires some change in the plan, some decisions are to be made. So the software actually informs the planner of such situations. So that is one of the very important output of the MRP system. And according to the action messages, the plan can be changed, or the order can be expedited, or some other actions depending upon the situation can be taken. So one of the inputs is MPS. We have discussed MPS in detail. So MPS drives the MRP system by providing the initial input for the item, so that we call the gross requirements. The inventory records, we will see one example of this in the following slide. So it is used to find out how many are needed. The quantities available must be considered. So what is the current status of the inventory of the item that we are talking about? So we need to know how much is at present available and how much is allocated. So allocated mean that we have sort of approved that component to be used for certain production in a certain period, but physically that inventory is still in the warehouse. So that is allocation. This type of information is dynamic and changes with every transaction that takes place. So that is an important challenge as well. This file, inventory record file, keeps on changing. So that is why we are calling that it is dynamic. So each transaction actually changes the status of this file. So for example, if we have 500 items in stock, and the order point that we have, for example, decided is, let's suppose 300, but there is a sudden issuance of this item that requires a quantity of, for example, 250. So the stock level immediately moves to 250. So that is something we call lumpy demand. So sometimes suddenly the level of the inventory changes. So it is very important to keep an eye on the status of the inventory of these items, because they keep on changing with every transaction. So there could be issuance, there could be receiving of the item, there could be allocations, there could be some other factors as well. So each item has a record, and all the records together form this file. So this is also called inventory record file or item master file, and this is a dynamic file. The third important input is bill of material. We will see it in one of the following slides, and the fourth is planning factors. So let's first see an example of this second important input, that is inventory record file. So this is an illustrative example that is showing the item record for part 10564. This is the gear housing. The component is gear housing. Units of measure are each, but there could be dozens or some other units as well. Order quantity is fixed order quantity equal to 50. And we have assigned some code to this, this item as well. The lead time is 3 weeks. And you can see some other factors as well. For example, last cycle counting for this component was performed on 22nd of March. So we will discuss in one of the topics in inventory management, what is cycle counting. Last receipt was on 1st April. So you can see here that on 1st April, we received 26 items. Last issuance was on 6th April. So you can see on 6th April, 23 items were issued. Year to date usage has been 190. Month to date usage has been 23. And you can see that although we have 17 items on hand, that is here from the column titled balance, we can see that we have 17 items, but 7 out of them have been allocated. So actually we have 10 items available that we can issue. There are 22 items on order as well. So that is what is called schedule receipt. So if we can track the order date of these 22 items, we can foresee when we will receive these 22 items. We don't have any plans for having safety stock for this item, and there is a scrap factor of 0.10. So that means that if you require 100 items, you would be ordering 110 to consider this scrap factor of 10%. So you can see there is a lot of information in this inventory record file, and with each transaction, there are a lot of changes that occur. So it is very important to have an updated inventory record file. Next, we have a very important point here actually is how we can number the parts. So there is this is a very important topic, very detailed topic, but there are some do's and don'ts. So for example, one of the important consideration is that you should assign one number to every part. It is important to use a single numbering system throughout the organization. If you use multiple numbering systems, of course, they can cause confusion. Use only numbers, and the shorter the better. There is a general thinking or understanding that we should use alphanumeric codes. You can use alphanumeric codes, that is not forbidden, but it is better to use only numbers because they are easy to use and interpret. Assign one trained person to manage the numbering system, and there are some there are important factors that should be avoided. So for example, do not use suppliers numbers because in your ERP record, you can sort of mix up the suppliers parts with your parts. So it is important to use some unique numbering system. So that is important. Avoid complex number formats. The basic purpose of this numbering system is to easily identify the parts. So they don't need to be too complicated. Do not reuse numbers from the retired item. So if you are not using some item anymore, so it is better to assign a new number to a new part rather than reusing the numbers of the items that are no more in use. Third important input is bill of material. Is a listing of all the sub-assemblies, intermediates, parts, and raw materials that go into making the parent assembly, showing the quantities of each required to make an assembly. One important thing that I feel missing in this definition is that other than the quantities, the level is also described by the bill of material. So in manufacturing sequence, actually at what level that sub-assembly or component will be required. The bill of material shows all the parts that are required to make one final product. So that is important to be. Then we use the process of exploding. That is nothing but simply multiplying the number of components that are required at each level to find the total number of components required for a certain quantity of the end item. But bill of material shows the parts and sub-assemblies required to make one end item. Each part or item has only one unique part number. So this is again re-emphasized here that you should use unique part number for each part. A part can be defined by its form, fit, or function. If any of these changes, then it is not the same part and it must have a different part number. So for example, if two products are the same, two parts are the same, but you just, for example, change material. The size and dimensions are the same, but the material is changed, so that will become a new part altogether. So similarly, if you change, for example, uh, some other important factor that distinguishes that part, for example, in certain cases, if the color is changed, so change in color actually identifies a different part, so that will require a new part. So what is shown here is not actually the bill of material. It is actually the list of components that will be uh, required to make a certain part table in this case, because this is showing one um, uh, sort of element of a bill of material, that is the quantity of different components required to make one table, but it is not showing the level. So you can say this is a very simplified bill of material. Again, unique part numbers are important to be assigned. So there are different formats to show the bill of material. Technically, what is shown here is also not a bill of material. That is something that you must have studied in your engineering drawing. So we generally call it product tree. But important point here is that this is a single level product tree or bill of material, because it contains only the parent and its immediate components. So that is why it is called single level bill of material. So the final end item, that is called parent, and its immediate components. So for example, we require 4 legs, 2 ends, 2 sides, 1 top, and a hardware kit. So that is why it is called single level product tree or bill of material. So in this case here, it is multi-level bill of material or product tree. So we have end item, that is table. It comprises 2 sub-assemblies, base and top. Base further consists of, for example, here 4 legs, 4 boards, 1 frame, and frame is a sub-assembly that consists of 2 sides, 2 ends, 4 legs, and glue. And top has 2 components. It is made up of boards and glue. And once again, you can see that each product or part has a unique code as well. So generally, this end product is assigned level 0. It is assigned a code 0. The immediate sub-assemblies are assigned a code 1. Then a code of 2 and 3. So the lower is the low level code, the higher is actually the level of that item. That, in other words, the higher is the code, the earlier that component or sub-assembly is required in the manufacturing sequence. And smaller is the number, the later that part or component is required in the manufacturing sequence. So these are the 2 pieces of information that the product tree or bill of material provides. How many components or sub-assemblies are required to make an end item? So for example, in this case, we need 1 base and 1 top to make 1 table. But to make 1 base, we require 4 legs, 4 boards, and 1 frame. And in order to make 1 top, we require 3 boards. And in order to make 1 frame, we require 2 sides and 2 ends. So in order to make 1 final product, how many sub-assemblies and components are required? And secondly, the level. At which level is each component or sub-assembly required? So level here means when in the manufacturing sequence that part or component is required. So again, the higher the number, the earlier that component is required. Now we are talking about the logic of ERP or MRP software. So important point, that is mentioned, that is shown here with the help of two figures, is that the product is the same. We are talking about tables, but this table has a code of 100, this table has a code of 150. So both are tables, but both are having different code because some characteristics will be different. For example, their top is different. So this table is having a top 023. This table is having a top 025. Although the base is the same in both cases. Similarly, the legs have a code 203. So they are the same. Bolts are also the same. The frames are also the same. Boards are different. 030 and 035. Similarly, the glue is the same, and so on. You can observe other parts as well. So the point that I want to re-emphasize is that you can store the information about the product in two ways, because then you have to recall from the software. So you are making a database actually of the products and component that will be there. So one of the ways is shown as in this slide. So you can store the information in the database in terms of multi-level bill of material. The final product is sub-assemblies and their components and so on. And the second possibility actually is to store the information in terms of single level bill of material. So we are talking about the same two products, table 100 and table 150. But instead of storing the information as multi-level bill of material, we are storing information about the products as single level bill of material. So we are showing just the immediate sub-assemblies for table 100. Then each of these sub-assemblies has a different single level bill of material. And then of course, each sub-assemblies of these sub-assemblies has another single level bill of material and so on. So both possibilities are there, but there is a food for thought, which of these two options is better. Multiple level or multi-level bill of material or single level bill of material. Which one is better? Generally speaking, this option, the second option is better. There are different reasons. We will discuss those reasons toward the end of this segment. But let's take a very simple example that, for example, we change the design of this first table. Or you can say we make a new variant of this design, and this table 100 has a top 023 and this has a top 025. And let's suppose we make a new design of the top of the table and we assign it a code 027. So if we make changes to this design, the information of this product in the database, then we will have to redefine it. But if we are having single level bill of material like this, we only have to change this single level bill of material. Here we will just assign a code 027 for the top. And from the database, we will, of course, we will define the top 027 and recall it here. And the rest of the bill of material will be automatically updated. So if it is not clear, we will discuss this point during the question answer session. Another form of bill of material is indented bill of material, and that is more commonly used. So indent is to sort of, with respect to Microsoft Word, you have also come to know this point that we give some spacing before typing. That is called indent. So for example, the part number 200 and 023 have the same indent in this case. And you can see that 203, 220 and 300, they have the same indent. So these three are at the same level. But you can see that these these four actually, 622, 411, 533, and 066 are written after giving some spacing. So that is clearly showing that these these three, 203, 220, and 300 are the components of 200, and 622, 411, 533, and 066 are the components of 30. And similarly, these two are the components of 023. So that is more clear from this description that these three are written at the same level of intent. So these are the sub-assemblies for the base. These four are written after frame, under the frame, and they are having the same level of intent. So they are the components for frame. And similarly, these two are the components for the top. And this base and top have the same intent. So in summary, the base and top are required at the same level. Legs, leg bolts, and frame are required at the same level. And these four are required at the same level. So we can say it in another way that we need base and top to be combined together to make the table. We need legs, leg bolts, and frame to be combined together to make base. We need slides, ends, legs, bolts, and glues to be combined together to make frame. And we need boards and glues to be used together to make the top. So let's once again discuss the low level code. So you can see that A is the end item. It comprises two sub-assemblies, B and C, and B comprises C and D. So you can see that C is appearing here as well as here. We have a low level code of 0 for A, 1 for B, and 2 for D. But what about C? Whether C will have a low level code of 1 or 2. Because it can have one low level code, it cannot have two low level codes. So for A, we will have low level code 0, for B, it will be 1, and for C, it will be 2. It is the low level code. So low level code is the earliest when that component will be required. So that is why we will have a low level code of 2 for C, not 1. And finally, we have some important planning factors. So one of them is the lot size or order quantity, the standard amount of an item ordered. So we can have fixed order quantity, we can have lot for lot, we can have economic order quantity. So that is the standard amount of an item that is ordered. The lead time for work orders can be based on an engineering estimate or historical knowledge of the time needed to complete a component. So that is for the component that are manufactured by the organization itself. And lead time for purchase orders can be based on an estimate or an historical average of the delivery lead time. So sometimes there are some issues in the production, and the production doesn't deliver the component on time, or if they are purchased, they are not delivered by the supplier on time. So in that case, we use safety lead time. So both these safety factors, safety lead time and safety stock, are important to be understood. So safety stock is about amount. Safety lead time was about, of course, timing. So if the lead time is, let's suppose, 4 weeks, but you know that there are delays, so you can have 1 week as safety lead time. So instead of ordering that part 4 weeks before it is required, you can order it 5 weeks before it is required. And safety stock relates to the amount of extra inventory deemed necessary to prevent stock out due to natural fluctuations in demand or supply, or to protect against forecast errors. So there are two types of uncertainties in supply chain. One is that uncertainty related to time, the other is related to quantity. So uncertainty related to time is addressed using safety lead time, and uncertainty related to quantity is addressed using safety stock. Scrap or material outside of specification that is not practical to rework. So when a process produces scrap, MRP increases the planned order release accordingly to account for this factor. So that is the basic point. So based on historical data, you know the quantity of scrap, so you can add that factor to the planned order release. So it is better to store product structure as a single level or multiple level bill of material in a computer. So as we discussed, it is better to store information describing the product structure as a single level bill. A series of single level bills is needed to completely define a product. In this case, we can avoid duplication. And secondly, the number of records and in computer system, the file size are also reduced. So we can come to this point if it is not clear. And the final point is that updating of bill of material is simplified. So that is something that we discussed with the help of example of the bill of materials of two tables. So let's solve a very simple example. Here we are having the product tree for product X and product Y. How many Ks are needed to make 100 X's and 50 Ys? So you have to do two things. First, you have to construct the appropriate single level bills and calculate how many Ks are required to make 100 X's and 50 Ys. So 100 X's and 50 Ys. So you can see from this figure that each X requires 2 Bs and each B requires 2 Gs. So that obviously means that each X requires 4 Gs. 2 into 2, 4. So 100 X's require 400 Gs. So 100 into 4 is 400. So each Y requires 1 L and each L requires 1 G. So 50 Ys require 50 Gs. So 50 into 1 is 50. So total Gs required are 400 plus 50. So this 400 plus 50. So 450 Gs are required and each G requires 2 Ks. So we require total 450 into 2, 900 Ks. So this process is called exploding the requirements. So bill of material told us how many components are required to make one end items. So based on those quantities, we have simply multiplied them together to reach the quantity of component K required. So this process is called exploding the requirements. So in summary, we saw that there are 4 important inputs to MRP. We discussed each of them, and in the following segment we will discuss the MRP process. Thank you.